Hey guys. Just give me a second. I'm gonna admit everybody into the class. How you guys doing this morning?
Great, thank you. How are you, Professor?
Good, thank you. All right. I'll just keep admitting as people join up. Anybody have questions about the homework from last night that they want to ask in particular? I have a couple that I'll go over if nobody has any questions, just to make sure that we're all on the same page about them.
I have a question for homework 1.1a. It's not question number 15.
Which one?
15.
15. Good. Yeah, that's actually one of the ones I want to go over too. Excellent.
Great.
Okay, so we'll go ahead and get started on 26. Okay, good. All right, so question 15 is a good one. So we've got, this is set up 5 over x ln of x dx. It's not obvious, right? When you look at this, like, this is supposed to be integration by substitution. What am I actually doing here? And it's a little bit confusing, but this is actually a really good example because this kind of a question comes up a lot in on exams. I've seen a question similar to this on like final exams and stuff like that. It's in the context of other things, but it's actually a really important thing to be able to recognize like what's happening. So we've got a 5, which is really just like a number. Like it doesn't really come into play and things. So what I'm going to do is I'm going to take the 5 out. And I've got 1 over x, and watch what I'm going to do. I'm going to say 1 over ln of x and then dx. So I'm just going to start separating things. You don't have to do this part, but it's just so we can visualize like what's actually happening and what are the pieces that we're trying to do. Okay, so let's remember, so substitution. So first off, like our first question, remember we're doing a toolkit, like we've got like increasing levels of complexity in the functions that we're trying to integrate. And then we've got increasing levels of tools that are going to help us handle integration on functions that are getting more complex. So when I see something like this, I can't just do the power rule. I can't think about like, I'm just going to do an exponential or some other function. I have to actually, you know, think about another tool in my toolkit. We also know that this chapter section is dealing with substitutions. That kind of gives us a clue. So let's think about what we have. So if we do substitution, right? So the question is, what am I going to substitute, right? So I've got x, and if I substitute u equals x, then my derivative is just 1. So that doesn't really help that much. I've got ln of x. Don't worry that it's 1 over ln of x. We're just going to think about what's the, you know, the most basic piece here. So this is ln of x here. So if my function is ln of x, okay, let's just try it and see what happens. If I take the derivative, my derivative for the natural log is 1 over x dx, right? Well, look at what we have. I've got 1 over x dx that's happening here. So let's rewrite this. So I've got 5, the integral. I've got 1 over ln of x times 1 over x dx, right? So this is what we have. Du equals 1 over x dx. I'm going to substitute this whole bit with du. This piece here, I'm going to substitute with u. U equals ln of x. U does not equal to 1 over ln of x. U just equals ln of x. Okay, so let's go ahead and do that substitution. So I've got 5 integral 1 over u times du. Okay, so this is our case. We have u to the minus 1 du. Okay, this is right. This is the special case where we can't do the power rule. We have to do the natural log of it, right? If I go to integrate this. So to actually evaluate this, don't forget you have to keep carrying that 5 through no matter what. So I'm going to integrate u du, and I'm going to go natural log the absolute value of u plus c, right? As though we're just integrating this as though we're a regular function, like without any kind of substitution. But now I need to substitute back. I have to substitute back. So u, remember, is equal to ln of x. So I'm going to substitute that back into here. So watch what I'm going to do. I'm going to say 5 ln absolute value of ln of x and absolute value then plus c. So you notice I don't have an absolute value around x right here. And that's because I didn't have it to begin with, okay? I was just taking the natural log of x. When I take the natural log as a result of integrating my function, right, I have to add the natural log. Okay, so then that's your solution. This comes up, this kind of problem comes up a lot because I've got 1 over x dx. It doesn't look like it. And I'll tell you a common mistake that people make is they say my u, the u is 1 over ln of x. Think about what's your innermost function, right, that you're just substituting for is going to be like a simple representation of that function. I'm not going to make it 1 over ln of x. I'm going to just make it ln of x, okay? Because look, I've got the derivative of the natural log right there already, okay? But this is a really good question because it comes up a lot. Okay, number 26. Okay, somebody wants, let me let you guys finish writing that down and then we'll talk about number 26. 26 is a good one. I also want to talk about, I think, let me see, look at the number. It looks like 19. I want to do 19 as well.
Sorry, would it be possible to go over number 23? Because there's, I think, the ln minus 1. I think there is that like little thing.
Yeah, that's, yep. And it's because in that one, actually, we're taking the natural, we're taking the absolute value of that one too. So that the minus 1, it isn't a problem. It just becomes positive 1. But we'll do that one too.
Got it. Thank you.
We'll just go in order. So somebody just asked 26. So you guys will have this one, okay? I'm going to scroll up here. Okay, so 26. So 26 says b of y equals 1 over y plus 1 over y squared plus 1. B of 1 equals 0. Okay, so we're looking for capital B of y is going to be the integral, right, of this whole thing here. So 1 over y plus 1 over y squared plus 1 dy. Oops, that's a y, dy. So now what we want to do is we're going to, okay, we're going to end up distributing this, right, the dy and the integral to both of these terms here. So 1 over y dy plus, whoops, that's a y, 1 over y squared plus 1 dy. Okay, so now when I go to integrate this, I'm going to get 1 over y is going to give me the natural log of the absolute value of y plus, this is, right, recognize this one here, this is our inverse tangent, right? And then I've got plus c that I'm dealing with. Okay, so this is just my general, and I have an initial value problem, so I can start thinking about this one here. So to get rid of c, so I'm going to go b, oops, sorry, there, b of 1 equals 0. So then everywhere I see a y, I'm going to put in a 1. ln 1 plus the inverse tangent of 1 plus c. So remember your inverse tangent, we have to think about what's the inverse tangent of 1. By the way, if you're going to do this to get a value on your calculator, make sure you're in radian mode when you're doing this stuff. Everything that we do in Calc 1, Calc 2, Calc 3, that's all in radian mode. Okay, so be careful if you're typing this into your calculator, make sure you're in radian mode. But often we're looking for things in terms of pi. So like if you give it into your calculator, but it gives you back a fraction, make sure maybe you can recognize that as, oh, that's, you know, let me just check what's pi over 3 or what's pi over 4. What is that as a fraction? So that you can give your answer in terms of pi. But let's think about it just for a second. I'm going to go off to the side. I'll do this in a different color so we can see it. Let's remember our inverse tangent. When I go to graph inverse tangent, I like to think about what's my tangent function, just my regular tangent function. So I'm going to limit my tangent function to minus pi over 2 to pi over 2, right? Because it's got, that's how we need to limit that in order to take the inverse tangent, so it's a function. So remember, when tangent is equal to 1, that's when the sine and the cosine are equal to each other, and that happens at pi over 4. Minus 1 at minus pi over 4, minus pi over 4. So then we're looking at, so our tangent function does this, right? I'm drawing this because it helps me visualize what my inverse tangent function looks like. inverse tangent. This is just for you. You don't have to like draw this out on a piece of paper. You don't have to do this like as part of your homework, but it helps visualize things. So when I take the inverse tangent, I've got now my vertical asymptotes become horizontal asymptotes. So I've got a horizontal asymptote at pi over 2, and another horizontal asymptote at minus pi over 2, right? And then now what happens is this function, there's 1, this is pi over 4. Let's see, here's minus 1, here's minus pi over 4. So my inverse tangent function does this, right? So now I'm looking at what's my inverse tangent of 1. My inverse tangent of 1 is pi over 4. Right? So that natural log of 1 is equal to 0. Inverse tangent of 1 is pi over 4 plus c. This is equal to 0. So my c is equal to minus pi over 4, right? Just from this equation right here. So I can plug that all back into here to get my specific solution. B of y equals ln of the absolute value of y plus the inverse tangent of y minus pi over 4 for our specific solution. Okay. So this, what I did here in red is just to help us visualize. You know, like maybe you guys already know this, or your calculator will give it to you in terms of, you know, fractions and in terms of pi. But when we're looking for answers on things, we're usually looking for values in terms of pi instead of some decimal number. Okay. 23 is going to be really similar, but we'll go through that one. You know, I guess you had a question about that because of the minus 1. And that one, 23 is gonna, the minus 1 is gonna go away. The negative part's gonna go away because we're taking the absolute value of it. That's why it's always helpful to get into the habit of putting the absolute value on the natural log, because it helps, you know, when you get into a case like 23. But we'll go through 23. You guys all have this okay before I turn the page? All right. Okay, so question number 23. So this one says P of W equals 5 over W minus 7e to the W plus 6 cube root of W. And we have an initial condition there. Okay, did I copy that down right? It looks like. Yep. Okay. All right. So now we're looking at capital P equals the integral of this whole thing here. So I'm going to go integral of 5 over W. I'm going to just distribute this as I go. dw minus the integral 7ew, that's an e, dw plus the integral of 6. And what I'm going to do is I'm going to convert this to an exponent already, just so I can start working with power rule, right? So I've got, this is, my exponent is minus 1 here, right? So this is the integral of 5w minus 1, right? So I need to be able to think about how I'm going to be handling that. Remember, I can't do the power rule on this one. This is my exponential function, and this is my power rule. Okay, so when I go to integrate this, right, I've got the 5, that's just my coefficient. W to the minus 1 gives us a natural log. Remember, we do the absolute value, right? Minus, there's a 7. Okay, my integral of e to the W is just e to the W. And then here I've got 6 that I'm carrying through, and then I've got this one. So this is going to become W to the 1/3, whoops, sorry, that's a third plus 1 all over 1/3 plus 1. Okay, so that makes this W to the 4/3 all over 4/3, and that's a plus C. So let's clean this up right here. So I've got 5 ln of W minus 7e to the W. So 4/3, right? I'm going to multiply by the reciprocal, so it's going to be 3. This is so 6 times 3/4. So it's going to be 18 divided by 4. I can, you know, clean that up a little bit. So what I'm going to get ultimately is 9 over 2 W to the 4/3 and then plus C. Okay, that's a 4. All right, so now this is P of W. Now we've got our initial condition. So I'm going to say P of minus 1 equals 0. So 5 ln, watch what happens. It's absolute value minus 1 minus 7e to the minus 1 plus 9 halves minus 1 4/3, right? So this is a cube root, so I can have a negative inside of my cube root, okay? So right here, this becomes the ln of 1, which is equal to 0. So 5 times 0, okay? And then this here is just a number. This is -7 all over e. We're going to leave it in terms of e. And then this becomes, right, this is the cube root of -1 is -1, but raised to the 4th power becomes positive. So it becomes +9/2 and then plus c. So I'm just going to combine things, right? And then ultimately, I think this was equal to 0. And I think when I combined it all, I got ultimately c was equal to 14 minus 9e all over 2e. And you may get something slightly different if you're cleaning things up or if you're combining your fractions a little bit differently. I've seen people write it like 7e to the -1 minus 9/2, right? If I distribute it, to each piece, it doesn't matter. I don't care how you want to represent it. They're the same thing. So then my total equation, oops, sorry, you can see that P of W is equal to 5 ln absolute value of W minus 7e to the W plus 9/2 W to the 4/3 plus, I'm going to leave it like this, 14 minus 9e all over 2e. I don't care if you want to add it in like that, that's fine. Okay. So watch your absolute values, because you're right. If you get to this point here where you're trying to take the natural log and you get a -1, it's going to give you, it's undefined, right? But remember, when you're taking the natural log, you have to put in the absolute value. Submit a PDF of a printed out version of the homework, or is writing it out on paper fine? Yeah, so it's a great question. So I'll tell you a couple things. If you have access to a printer, printing it out and then working on it will give you sort of a more solid reference point where you're actually able to see what the questions are and see what the answers are, because it'll help you study for it. But you don't have to. I would say, I've had students in the past who just look at it on the screen and then they write down all their answers on a separate piece of paper. Make sure you write out, this is chapter 1.1, question number 1. If you're just going to write it on a piece of paper, it'll be very helpful for you to also write out first what the question is, right? You don't have to write the whole, like if it's like as we get along, when we move into like more complex stuff and we get like bigger instruction sets, you don't have to do that. You just have to write like maybe what the equation is and what it is you're doing. And that way you'll have some kind of reference so that when you go back and study for it, you'll see what the question is and then what your answer is. So that'll help. But you absolutely, you don't have to print it out and then write it on the homework, but it does help for you to see what the questions are. I've also had students who, have iPads. They just want to, write it on the iPad, using their electronic stylus. That's totally fine too. The only issue is if I have like compatibility issues where I can't read it, sometimes it uploads as garbage. I don't know why. I'll let you know if I can't read it because it's like a compatibility problem. And then you'll just have to take a picture of it and then send me those pictures. So yeah, it's fine either way. You don't have to print it out if you don't want to. Okay. All right. You guys all set with these questions here? Okay. Okay. Good questions. So we were talking about substitution last time, and I think what I'll do is I'm going to go through, we've got the other lecture examples to finish, and I want to make sure that you guys get these lecture examples before we move on, so that just to complete out the set, because some of them, they have good ideas in them, and they kind of illustrate different things. So why don't we we'll go through these lecture examples for the rest of, this is the lecture examples for chapter 1.1 that we started yesterday, that I said we had like a couple more to finish, and we'll finish them up today before we start on the next portion of chapter 1.1. So let's go through and take a look at our lecture examples. So I'm on lecture example number 6. So this is still now about substitution. Okay, so we're looking at these things, right? And I'm looking at, I want to integrate 8x all over 4x squared plus 1 quantity squared dx, okay? So when I go to substitute, I need to be thinking about remember it's f of g of x. So I want to find what's that g of x, that function that's on the inside, okay? So I've got this function right here, 4x squared plus 1. Don't worry that it's quantity squared, okay? If you try to take it in its complex form, I've got this quantity squared, it's going to be a nightmare for you to try to figure out how you're taking the derivative and doing substitution. Always be looking sort of on the inside. What's your inside function that you're trying to do? Also, another clue that you want to look at is, remember when you do substitution, you're going to be taking the derivative of the function that you're choosing to be your u, right? If I have x squared, the derivative of x squared is x, right? I mean, it's 2x, but in its most functional form, it's x, right? So I've got an x here, and the derivative of x squared is going to be x, right? So I know, okay, that this is going to be a derivative of this here. But if I do 4x squared plus 1 quantity squared, the derivative of that is much more complex than just x. So these are like clues in your mind when you're trying to think about, like, what am I going to choose from my function that I need to substitute for? Okay, so let's do it. So u equals 4x squared plus 1. So remember, not quantity squared. We're keeping it the most simple inner function. So that means our du is equal to 8x dx, which is what we have right here. It's not always going to be the case that it's going to line up so nicely, but in this case, we have it exactly. Okay, so now what I'm going to do is I'm going to substitute that in. So this is going to become, so 8x dx gets substituted with du. 4x squared plus 1 gets substituted with u. So I've got 1 over u squared times du, which becomes, I'm going to write it like this, u to the minus 2 du. Okay. Now remember, when we were talking about, doing things like with the power rule, we had exceptions. There's that p, power equals minus 1. Well, I've got power equals minus 2. Well, minus 2 is not a problem, right? It's just a power that I can just do the power rule with. Okay, but let's do it out so you can see. So when I go to integrate this one with the power rule, I'm going to get u to the minus 2 plus 1 all over minus 2 plus 1. And I'm going to add in my plus c. I'm spelling this out so you can see what it is, because this is a common mistake that people make. So when I do this minus 2 plus 1, I get u to the minus 1 all over minus 1. This is plus c. So this is equal to minus 1 over u plus c. Okay, right here. Now we need to substitute back. Remember, u was equal to 4x squared plus 1. Okay, so I'm going to substitute that back into here. It's going to become minus 1 all over 4x squared plus 1, and then I have a plus c. Okay. Everybody see how we did that? Be careful, it's a common mistake people make. 1 over 4x squared plus 1 quantity squared. But then when you go to take the derivative of that, it's much more complex. Okay, remember, you're looking for a simple piece that you're trying to just substitute for, an inner function. Think f of g of x. What's my g? Okay, so let's try this one here. 18x squared times 3x cubed plus 3 quantity squared. And you're going to be tempted to, FOIL this out and then multiply, distribute, and then go ahead and do the, the linearity rule. The whole point of what we're trying to do here, now technically that's correct, but the point of what we're trying to do here is recognize that there's substitution. So like, for example, on a final exam, you may get a correct answer at the end, but we only give like a point or two for the correct answer, and a lot of it is just your method. Okay, so if you don't use substitution, you may get a point for the correct answer, but you're going to lose all the points on the method. Okay, so think about what it is that you're trying to do here. So let's remember, our more complex function is, I've got this cube, x cubed, and I have an x squared, right? So let's think about it. If I were to take the derivative of x cubed, I'm going to get x squared, right? So I've got an x squared, which is a derivative of this right here. So if I'm seeing a derivative of a function, that helps give me a clue about what I should use as part of my substitution, okay? So think about that. Okay, so let's go like this. So u equals 3x cubed plus 3. Not quantity squared. Remember, we're doing the inside function, right? That's f of g of x. I'm trying to substitute for my g. So my du, right? So let's do this. This is going to be 9x squared. The 3 goes away. This is dx, okay? So you can do a couple things here. Sometimes if it doesn't line up, look, this is 18 and I've got a 9. What I'm going to do is I'm actually going to work with x squared dx. So I'm going to divide this by 9, divide this by 9. So I'm going to get du over 9 equals x squared dx, okay? Which also means what I'm going to do is I'm going to rewrite this to bring the 18 out, and I'm going to go 3x cubed plus 3 squared times x squared dx. And I'm just rewriting it, kind of grouping it so I can visualize. I've got an x squared dx, I've got an x squared dx. I'm going to substitute that. This is going to get substituted with du over 9. This bit here is going to get substituted with u. Okay, so let's go ahead and rewrite this. This is, you know, a method, right? If you've got, maybe you learned it in high school or other places with substitution, you're going to multiply, you're going to divide. You know, it's up to you if you want to do that. I'm just trying to teach it in a way that I think is, you know, kind of simple and methodical. So let's rewrite this. So this is going to be u squared, right? And this is times du over 9. Okay, this 1 over 9 I can bring out. So this is 18. I'm just going to show you all the steps. 18 over 9 u squared du, okay, which is just 2 u squared du, right? Okay, so now this is just the power rule. Okay, so we're going to be able to integrate it as we go. So 2, this is going to be, I'm going to increase this power by 1. So this becomes u cubed all over my new power, and then plus c. Sorry, that's a plus. Okay, now let's substitute back. Okay, so I've got 2/3. I write it out like that. So my u was equal to this right here. So I'm going to substitute 3x cubed plus 3 quantity cubed and then plus 3. And I'll put a box around it. Okay.
Professor,
What's up?
is there like, I'm just curious, when you had the du over 9 and the 18 on the outside, you just like put the 18 over 9. Is there like a reason for that, or like how did you just do that?
Yeah, because right here, right? So this 9, this du, this is equal to du times 1/9, right? Remember, like constant terms, these numbers, right? The 1/9, just like how I brought the 18 through the integral, the constant terms, right? These numbers can just be brought through the integral. They just become a multiplier that I'm going to multiply my final answer by. So I brought the 18 through already, right? And then when I substituted x squared dx with du over 9 is just 1/9 times du. So I brought the 1/9 out. So this is really what I did was 18 that was there before times 1/9, right? Because I brought the 1/9 through the integral, and it becomes a multiplier that I'm going to multiply my answer through. So 18 divided by 9 is just 2. Does that make sense?
Yeah, sorry, thank you.
It's okay. I know there's a lot of little steps. You know, I find this method, like I said, I know that there are other methods. You know, we've got this factor of 2, I can multiply through, whatever, you know, whatever, if you've learned it differently, and you kind of can think it through differently, that's fine. I like this because it kind of shows the steps in my thought process of like what I need to do and how I need to substitute. So that's why I like that method. You know, but if you're arriving at this differently by just multiplying by 2 because you recognize that that's 9 and you have an 18 and you need to multiply by 2, that's fine. But I like this way because it shows exactly what I'm trying to do. Okay, so example 8, let's talk about 20x times the sine 5x squared minus 3 dx. Now, this is an interesting one because as we're going to see in just a little bit when we get into 1.1 part 2, okay, 1.1b, which is what do I do? How do I integrate functions that have 2 functions that are being multiplied together? Remember when we said, well, we can't do linearity if functions are being multiplied, so I have to have another clue. So you're going to be tempted, right, when you get these, when you have a whole set of tools in your toolkit for how do you process integrals, you're going to be tempted to use, you know, one or the other, but always start with the most simple method first and thinking about how you want to be able to process this stuff. So 20 times x, and look, x is a derivative of x squared. Right? When I take the derivative of x squared, I'm going to get x. I mean, there's a constant multiplier, but still, x is a derivative of x squared. So that means I have a derivative of my inner function here. Okay, so that means I don't have to do anything overly complex. I can think about substitution first as a first path. So I'm going to think about my inner function, my g of x, right? The f of g of x as being 5x squared minus 3. Let's see what happens. So u equals 5x squared minus 3. Now I need to take the derivative. Du equals 5 times 2, right? That's 10 x dx. Okay. So again, this is a case where I have 20x, but I have 10x here. So what I'm going to do is, just to keep it more simple for myself, I'm going to rewrite this. I'm going to bring the 20 out front. I've got sine of, oops, sorry, there's a 5x squared minus 3 times, I'm going to write this as x dx, just to keep it, more simple for myself. Now I'm going to divide by 10 here, So I'm going to get du over 10 equals x dx. The x dx, watch what we're going to do. So I'll put this in green. So I'm going to take this block, x dx, there's an x dx right there. I'm going to substitute du over 10, which is 1/10 times du, in for x dx. Okay, and then I'm going to take this, my u, and I'm going to substitute it into here. Okay, and then I have a 20 that's hanging out front. So let's rewrite this all now. So I've got 20 times the integral of sine, we're substituting in here, this is u, times, I'm going to substitute in here, du over 10. Du over 10 is 1/10 times du. So I'm going to bring the 1/10 through my integral, make my life more simple. So this is 20 times 1/10 times the integral of sine of u du. Okay, right, 20 over 10. So this is just 2 sine of u du. Okay, looks much more simple, right? That's the whole point of substitution, is that it's going to simplify a more complicated integral. Okay, so when we go to do this, let's remember, right, when we go to integrate sine, so I've got the 2 hanging out from before, and I've got integration of sine is minus cosine of u, and then don't forget your plus c. I put the parentheses there to remind me this is actually a multiplier. So I'm going to go minus 2 cosine of u plus c before I forget, because you don't want to accidentally add it thinking, oh, this is 2 minus, that's wrong. Okay, it's a multiplier. All right, so let's substitute this back. And I'm saying I've seen these mistakes, on quizzes, because you're going fast and you forget. Substitute, so u equals 5x squared minus 3. I'm going to substitute that back in. So minus 2 cosine 5x squared minus 3, and then plus c at the end. And I'm going to put a box around it, so that when your teacher grades it, they know where to look for the answer. Okay. So I'm trying to tell you my thought process as I'm working through these problems, and kind of take it step by step and think it through, what it is that we're trying to do. Okay. So what I'm going to do is I will scan in these lecture notes for 1.1 part A. I'll scan them in later today, and I'll upload them to our Canvas page later today. So probably, by 3 o'clock today, I'll have our lecture notes scanned in, and I'll put them up there so you guys can take a look for that. Okay. You guys good with this last example here before we move on to the next part of 1.1? Okay. All right, so this is chapter 1.1. We'll call this chapter 1.1 part 2. This is what we call integration by parts. Okay, this is another tool in your toolkit. This is a very powerful tool in your toolkit. So remember, like I said before, we're building up a set of tools for us to be able to analyze and process different types of functions that we're trying to work with. Our first line of defense was just integrate it using the power rule, or using our simple trig functions or exponential functions. If that doesn't work, see if substitution will work. Okay, if substitution isn't going to work because it's not a derivative that's being multiplied, then integration by parts is the next set that I should be thinking about. Okay, the next skill set I need to be thinking about. So integration by parts comes from our product rule in differentiation. Okay, just like our substitution comes from our chain rule in differentiation, the integration by parts comes from our product rule in differentiation. Okay, so let's remember what the product rule is, right? So I've got two functions. I've got u of t and I've got v of t. Say, for example, right? u times v, and then I want to take the derivative of these functions. They're being multiplied together, u times v, right? And I want to take that derivative. Well, there's a whole way that I need to combine this derivative. Remember, we did it, we talked about different things. It was the derivative of the first times the second plus the first times the derivative of the second. And it doesn't matter, you're adding, so you could do it in either order, right? But you basically got the derivative of the first function times the second function plus the first function times the derivative of the second function. I'm going to start writing this in terms of du and dv because that's the form that we're going to put this in when we talk about integration. So let me just rewrite that. So instead of u prime, I'm going to call this du, and this is times v, plus this is u times, instead of v prime, I'm going to call this dv, okay? And this is still, I'm going to call this now dt of u times v, okay? So now this is our product rule for differentiation. Okay, but now let's do this. So if I'm going to integrate both sides, what happens if I integrate both sides? So let's do it. So I've got integral of d dt of u times v equals the integral, I'm going to write it like this, v times du plus the integral of u times dv. Okay. All right, let's see. So if I take the integral of a derivative, right, these two are like two sides of the same coin, they cancel each other out. So I'm basically just dealing with u times v, right? And then here, okay, what I'm dealing with is I've got integral of v times du plus the integral of u times dv, okay? So now what we're going to do is we're going to rearrange this a little bit, right? Because what I want to do is I want to be able to solve, okay, for this bit, and then plug this into my equation. Let me just rearrange it. Rearrange this, and so basically what we're going to get is we're going to get the integral of u times dv equals uv minus, oops, sorry, v times du. Okay, so this ends up being what we're given in our function, and these are the bits that we're solving for that we can then use to solve for this part right here. Okay, so this is our integration by parts equation. Okay, and then I'll write this out. This is what we're given, and this is what we solve for to get the solution, because I can't just integrate u times dv because, you know, the function, it doesn't lend itself to substitution or to, you know, integral with power rules or whatever. So I have to be able to rearrange stuff and solve it in pieces and then put the pieces back together again. So integration by parts, let's just talk about what we need to do. So in terms of what we need to do, we've got two functions that are being multiplied together, and we're taking the integral of this product, right? We're multiplying two functions together, and we're going to take the integral of that product. Okay, so I need a set of skills that are going to help me do that. One of the functions is in a derivative form, right? That's our dv, and the other function is not. What we have to do is we have to choose u and dv correctly. We're going to go through and we do examples. We're going to choose incorrectly so you can see what it looks like, and then we're going to choose it correctly so you can see what that looks like too. Okay, so you can think about it like this, right? So I'm going to assign, I will assign myself, I'm going to assign one of the functions as u, and then I have to take the derivative to get du. Okay, I'm going to assign one of my functions that are being multiplied together as dv, and I'm going to take the integral of dv to get v, right? So I choose what's u and what's dv, and then I take the derivative and I take the integral, and that's going to give me the other pieces that I'm going to put into my puzzle, and then I'm going to work it from there. Okay. This is like our steps. And then when we work through examples, you can start to see how it'll all come together. And we're going to gradually increase our level of complexity on the examples. My suggestion for you is while you're learning this, especially, and I do this in all of my homework problems and stuff, I write this down. So I've got this problem and I write down uv minus the integral of v du. It helps me remember what's my formula. And it also kind of triggers, like, what do I need to do? It helps me start to remember what I need to do my process. Okay, because when you start getting these problems, right, it can be too much to think of, oh, okay, let's see, I have to assign one of them. What do I have to assign? What do I have to do? But if I write down the formula first, it gets my brain moving in a direction. And then I start to remember what I have to do after that as a process. Okay, so I've got my lecture examples I'm going to start taking a look at. This is lecture example 1.1b. I'm going to look at example number 1. So I'm going to take the integral of z times e to the z with respect to z. Okay. Now remember, let's do our checklist, right? For we've got our simple skills tools, and then we've got our more complex tools. So I have an exponential function. I've got maybe a power function. Well, I can't do linearity because they're being multiplied together. So if they're being multiplied together, I can't just do, power rule or exponentials or whatever. So let me think, maybe substitution. Well, z is not a derivative of e to the z, and e to the z is not a derivative of z. So I can't do substitution, right? You see the checklist that we're working through in our mind, okay? Now, then my next trick then is integration by parts. Okay, so if I'm thinking integration by parts, the first thing I'm gonna do is I'm gonna write down uv minus integral of v du, okay? Which means I need to start thinking about what am I gonna assign as u and dv so I can derive du and v. Okay, so what we're gonna do is I will do, I'll make the bad choice first, and I'll show you how, as we work it through, how I realize that that's the bad choice of assigning u as this and dv as that. Okay, so let's try it. So I'll tell you, I'm gonna make the bad choice first. Okay, and this happens, right? When you're working through functions, like when you do the homework or when you work through stuff, I know that there's some kind of mnemonic that people like to, to remember, like, how do I, choose which function is which. A lot of it is just practice, and I'm not gonna, I can't remember the mnemonic. So I always just remember what are the things that I look for, and I go down this path and it's not the right one, and then I have to backtrack and try the other one. So we're gonna ask ourselves questions along the way that will tell us whether or not we're making the right decision. Okay, so my bad choice. So I'm going to go u equals e to the z, which means when I take the derivative du, I've got e to the z dz. I always like in my mind to think about when I take the derivative, it should make the function more simple, right? Well, this didn't change anything. When I took the derivative, it stayed the same, right? Because that's the nature of our exponential function. But let's roll with it. So my dv then is what's left over. So if this is u, then my dv is z dz. Now I have to integrate this in order to find out what v is. So v is going to be the integral of z dz. Well, that's going to be z squared all over 2. Don't worry about your plus c. We're going to add the plus c at the very end after we're finished with our integration by parts, okay? All right, so already I'm seeing this is more complex than I started with, but let's go ahead. I'm going to put it into the form uv minus integral of v du. So u times v, so it's going to be e to the z v 1/2 z squared minus the integral z squared over 2 times du is e to the z dz. Well, look at what I've got. Z squared over 2 times e to the z. That's more complex than z times e to the z. So I'm thinking more complex. Maybe I'm gonna stop. So stop, switch, and I'm gonna switch. So correct choice. I did the wrong choice first so that you can see why it was wrong. So, okay, so I'm going down this garden path. It's more complex than the function that I started with. Maybe I'll switch my u and my dv and I'll try something different. Okay, so I'm gonna switch it. So my u now is gonna be z. So my u is gonna be z. That means when I take the derivative du, I get 1 times dz. Already I've made it more simple, right? I've gotten rid of a variable, which I like when I'm doing this stuff. So now I'm going to go dv is the other function, which is going to be e to the z dz. When I take the integral to solve for v, I'm going to get integral of e to the z is just e to the z. It didn't change anything, but I made things more simple right here, which is good. All right, so it's promising. uv minus v du. I'm going to plug things into place. So u v minus v du. Nice. It's more simple. All I'm doing now is integrating e to the z dz, whereas before I had two functions being multiplied together. So I've made it more simple. So it was probably the correct choice. And it was the correct choice. All right, so let's go ahead and do this. Don't forget, this is part of your answer. So what I've got is z e to the z minus, I'm going to integrate e to the z, which is just e to the z. Now we're going to add in our constant term. Okay, you can factor out e to the z and make it look pretty, or you can just leave it like this. My suggestion is leave it simple, you know, like that. Don't worry, because sometimes what can happen is you get the right answer here, you factor things out, you try to combine things, you make things look pretty, but then you make a mistake when you're doing that. And then I have to take off points because you got the wrong answer. So leave it like this, it's fine. Okay, so this is good. Everybody see how we made a bad choice, decided it was more complex, so we stopped and we switched our variables and we made it, we can see that it's making it more simple, so we're going to work from there. Okay. So I'm going to scroll down. Example 2 is really similar to this one. I'll give you a hint what's going to happen, right? This is z squared e to the z. So this is like basically where we were here, okay? This right here, this problem is going to require us to do integration by parts twice, which is totally fine. We can do integration by parts as many times as we need to in order to be able to integrate a function. We just have to keep track of all those pieces, especially that u times v, all those pieces that we're accumulating every time we do the integration by parts. So let's do an example where you can see what that looks like. Okay, so this case, right, I'm not going to show you the bad choice. I'm just going to go right into the correct part. All right, so now let's go ahead and calculate it. So I'm going to say u equals z squared. So my du is going to equal 2z dz. Okay, my dv is equal to e to the z dz. So I need to integrate both sides to get v. It's just e to the z. Okay, so we're going to put this together into integration by parts. Remember uv minus integral of v du. I'm going to plug that into here. Okay, so my u, z squared, my v, e to the z, minus the integral of v, e to the z, and my du is going to be 2z dz. Okay, so I'm going to bring the 2 out. Let's rewrite this down here. So I've got z squared e to the z minus 2 times the integral of z e to the z dz. Right, I just brought the 2 outside my integral right there. Okay. So now I need to do integration by parts. Again, the part that gets tricky is I'm going to do this integration by parts, but watch, I've got a negative and I have a number that I need to multiply through. The negative is the tricky one because when we do the integration by parts, I'm going to get 2 pieces, right? The uv minus integral of v du, and I have to distribute that negative. I use a lot of parentheses to help me keep track of stuff. So what I'm going to do is this. I'm going to say my u is equal to z. My du is equal to, take that derivative, dz. My dv is equal to e to the z dz. I need to take the integral to solve for v, is e to the z. So now I need to go uv minus integral of v du, but right here. Okay, so watch what I'm going to do. I'm going to remember I've got this bit here I have to bring down. So I've got z squared e to the z minus 2. I'm going to do a big bracket, parentheses. Now I'm going to go uv minus integral of v du for this bit right here. So u z v e to the z minus the integral of v e to the z, and then du dz. Close bracket. Right, the bracket signifies I have to multiply by -2 when I'm done. Okay, so let's go ahead and I'm going to show you the mini steps. So z squared e to the z minus 2 times the bracket. This is z e to the z minus e to the z. We'll add the plus c in at the very end. We'll do the plus c right now. Okay, so let's go ahead and distribute my -2 here. So this is going to be z squared e to the z minus 2z e to the z minus minus becomes plus 2e to the z plus c. See how it's important to have the bar through your c, otherwise I've got 2 times z. It'll become confusing when you take a look at it. Okay. And then leave it. You can't combine it anymore anyway, because I've got a z squared, a z, and no z right there. I mean, I suppose I can, you know, factor out an e to the z, but leave it. Okay, keep it more simple. Oops, sorry. You guys have questions on these two examples here for the basic integration by parts? We're going to start increasing the complexity of what we're trying to do. Okay. Right. Okay, example 3, we're going to do ln of t dt. It seems like, why can't I just integrate that normally? Well, that's a great question, because let's do it. So I can't do the power rule, right? There's no power in there, it's ln. I can't do substitution, right? Because I don't have a derivative here. Be very, very careful. A common mistake that I see when people see this, the integral of ln, they get it confused with the derivative and they say that's equal to 1 over t. Be very careful, because 1 over t is the derivative of the natural log. We have to find the integral of the natural log, okay? To integrate the natural log or any log, we need to use integration by parts. It doesn't seem like we should have to, right? Because it's just, where are the two functions? Here's one function, here's another function. 1 times dt is the function, okay? So again, we're going to go uv minus integral of v du to remind us of what the formula is and what we need to do. So how do we choose u? Remember, I have to take the derivative of that. So if I say u equals dt, if I take the derivative, I'm going to get the second derivative of t, right? So that's your clue. This is ln of t. When I take the derivative, right, it's going to be, the derivative here is 1 over t dt. Okay. What's left over is my dv equals dt. And I take the integral of both sides, so v equals t. Okay. Now I'm going to substitute all those in here. So I'm going to get u ln of t times v minus the integral of t times du, 1 over t dt. T times 1 over t, these cancel, right? So I'm basically just getting dt, right? So when I go to integrate that, so basically I'm looking at, I'm going to put this together, this is going to become t ln of t minus t, and then don't forget your plus c. It's helpful to remember, right? This is the integral of the natural log of t. Okay, it's like an equation, right? And you need integration by parts in order to do it. Okay. Okay. All right. We'll go into this one here. So we've got this ln of t dt, and we've got t to the 5, right? So remember, I'm going to need to do integration by parts, uv minus v du, because I've got two functions being multiplied together. Well, I need to start thinking about how am I gonna combine this? So this is kind of counterintuitive, because I always said, well, if we assign this one as our u, when we take the derivative, I get, right? So if I go, let's do this, I'll tell you we're going to do this incorrectly. So we'll do incorrect. This is our wrong version. So if I say u equals t to the 5th, then my du equals 5t to the 4th dt. Well, that seems more simple, right? But then that means my dv is equal to ln of t dt. But then when I go to take the integral, I have to do integration by parts, which makes it more complex, right? So maybe I'm going to do something. I need to think about that differently. Okay. So it's counterintuitive, because we think it's going to be more simple to assign this here and reduce the power. But because we have a natural log, what I'm going to do is this: u equals ln of t. So my du, right? When I take the derivative of the natural log, I get 1 over t dt, which is nice, right? Because it actually gets rid of my natural log and it brings it into just t, okay, just t format. Okay, so now that means my other function, dv equals t to the fifth dt, sorry, that's a t. And it seems counterintuitive because I'm going to increase the power, right? So my v equals 1/6 t to the 6. Okay, remember your power rule, you've got to divide by that new power. Okay, so now I'm going to put these together here, okay? So this is going to be u times v, so u, ln of t, times v, 1/6 t to the 6, minus the integral of v, 1/6 t to the 6, times du, which is 1/t dt. Let's make this, we'll clean this up a little bit. So it's going to be 1/6 t to the 6 ln of t minus, I'm going to bring the 1/6 out. Now I'm going to get t to the 6 times 1/t dt. Now watch what's going to happen. This t is going to cancel with one of those, so I'm going to get t to the 5th. So this becomes minus 1/6 integral of t to the 5th dt. Okay, now be very careful. I've got a 1/6 here already. I have to remember that's my multiplier. So let's bring this down. So this is 1/6 t to the 6 ln of t minus the 1/6 that we had there before. Keep it, right? Now I'm going to do power rule. Right, so t to the 5th becomes t to the 6 all over 6, and then my plus c. 1/6 times 1/6 is 1/36. It's a common mistake. People think, I've got the 1/6 there already. I don't need to multiply. It's a multiplier, okay? Which is why I always bring these down and keep things in parentheses to help keep me honest about remembering I need to multiply these things through, okay? Let you guys finish writing that. The last example we're going to do is kind of a trick example. You have a homework problem that looks just like this. So this will help you with the homework. Every year when we do a final exam question for integration by parts, this type of, the next example, this type of problem comes up, and then it's sort of debatable whether or not, you know, we should have this on the final exam, because it's like you need, it's kind of a trick how you're thinking about how to solve it. Okay, but we'll go through it step by step. You guys okay with this one now? Okay. All right. Okay, so e to the x cosine of x dx. And I'm going to use integration by parts on this because I've got two functions. I can't just integrate. I can't do substitution. So I've got it to uv minus integral of v du. Okay, so there's a trick in doing this, because remember how I said when we take the derivative, I want it to be, you know, more simple. Well, we'll find in this class in particular, e to the x has an infinite number of derivatives, right? Cosine of x has an infinite number of derivatives. Okay, e to the x has an infinite number of integrals, so does cosine. These functions are special classes of functions that, you know, they basically, they have an infinite number of derivatives and integrals, right? So, so taking the derivative isn't going to make things more simple. So I need a different way of solving this. So I'm just going to tell you right off the bat that there's a trick solution. Okay, so we're going to start working our way through and thinking about it. Okay, so I'm going to assign, I'm going to go u equals e to the x, right? So that means my du equals e to the x dx, and that's okay. Okay, my dv is what's left over, cosine of x dx. I take the integral of both sides, so that gives me v equals sine of x. Okay, so let's go ahead and put that together into our equation here. So what I'm going to get for my uv minus v du is this. So my u, e to the x minus, oh, sorry, whoops, sorry. V, where's my v, sine of x, minus v sine of x times du, e to the x dx. Look at what's happening. Can you recognize what's happening? I'm kind of where I was, right? E to the x cosine of x, e to the x sine of x. Okay, so we can start to see we're starting to develop a problem. So I need to do integration by parts again. When you're dealing with the case on integration by parts where you have two functions that have infinite number of derivatives, an infinite number of integrals, then when you do integration by parts again, keep the assignments of u the same. So again, when I do integration by parts, I'm going to again say u equals e to the x. Okay, and then I'm going to integrate sine of x. So let's go ahead and do that. So my next set is going to be u is going to be e to the x. My du is e to the x dx. My dv equals the sine of x dx. And I'm going to take the integral of both sides to get v is equal to minus the cosine of x. Okay, so now we're going to put these in, but watch, I've got this bit that I have to remember to carry through when I do integration by parts again. So I'm going to say, this is what I'm carrying through from before. So I'm going to go e to the x sine of x from before minus, right? I'm going to put the brackets, e to the uv minus integral v du. I'm going to do that again here. So u e to the x times v minus cosine of x minus the integral of v minus cosine of x times du e to the x dx. There's going to be a lot of things to keep track of. Okay, so let's start. We're going to distribute our negatives and then see what happens. So I'm going to get e to the x sine of x minus minus becomes plus e to the x cosine of x minus minus positive but negative here, right? So I've got 3 negatives. So that makes this minus e to the x cosine of x dx. Everybody see how I got to this point right here? Okay, use parentheses when you're doing integration by parts the second time because you have to keep track of your negative. I have to distribute my negative. The negative has to be distributed here and to here. Okay, but I've got a negative already, so I have to be very careful about all those negatives. Okay, make sure I get the sign right. Okay. All right, so look at what's happening. We are back where we started from. That's our original equation, right? So our original equation is, I've got this, let me just write it all out from the beginning. So I've got e to the x cosine of x dx equals, I'm going to write this over, e to the x sine of x plus e to the x cosine of x minus the integral of e to the x cosine of x dx. Here's what the trick is. I'll tell you, I'll just write it out here. Here comes the trick. It's not really a trick. It's just a different way of thinking about it. So we're accustomed to thinking, right, I'm going to solve this for an answer, okay? But when you're dealing with these special class of functions that have an infinite number of derivatives, you need to remember that you're dealing with an equality, which means that I can operate with both sides of the equation, okay? This isn't an identity where I have to just hold one side constant and then work the other to get them to equal, okay? This is an equation. So I'm going to start dealing with this as a block, okay? As like a variable, you can think about it. So what I'm going to do is I'm going to combine, I'm going to add this to both sides. So I'm going to add integral of e to the x cosine of x dx. I'm going to add e to the x cosine of x dx to both sides of the equation. So it cancels out here. And I have 2 times the integral of e to the x cosine of x dx equals this thing here, e to the x sine of x plus e to the x cosine of x. Okay. But my question, my original question was, what's 1 times the integral of e to the x cosine of x? So I'm going to divide both sides by 2, and I'm going to get integral of e to the x cosine of x dx equals divided by 2, and then I'm going to add in my plus c. Okay, this is, we call it a trick. It's really just expanding our mind to think about this as both sides of the equation that I'm working with, okay? And then also thinking about this here as a block, like a variable that I'm going to manipulate, okay? These things where I have these special class of functions, e to the x cosine of x, any kind of like exponential and a trig functions where they have infinite number of derivatives, okay? I have to start thinking about when I do this integration by parts, if I'm not careful, I'm going to end up back where I started from. Like if you did integration by parts again, you're just going to keep accumulating all this stuff. That's just a repeat of what you had before, right? You're back where you started from. If you're back where you started from, then think about how you can manipulate both sides of the equation to solve for it, almost like indirectly, right? So I'm solving for it, but this is the correct answer. Okay. It's kind of a trick. You, I think, have a homework question like this tonight. Okay, guys? So I'm going to let you guys go. Can we replace the initial equation with the variable? You know, I get what you're asking. Can we replace it with a variable? And we're thinking about it like it's a variable, right? I would be very careful about doing that because you're already doing a substitution where we have u and v and dv and du, right? And then if you're going to substitute it with a variable so that you can kind of think about, oh yeah, that's that variable again, and I'm going to combine the variables on both sides. If you wanted to, if that helps you make it more simple to think about in your mind how you're going to combine those, just be very, very careful because you have to substitute it back in the end, right? You can't leave this in terms of like W equals this whole thing. You have to remember to substitute it back, okay? I would say I would hesitate against that because you're already doing U and V as substitutions. But if you find it easier to do that while you're learning this stuff, then, you know, go ahead. But just be very careful that you substitute all your variables back at the end, okay? All right, you guys, I'm going to let you go because we're at time, and I'm going to scan in this lecture examples, and I'll upload that one to our Canvas page later today as well. Okay, have a great day, you guys, and have a great weekend.
Thank you. You too.
Take it easy.
Professor.
Thank you.
Take care. Bye, guys.
Thank you, Professor.
Take care.
Thank you.
Bye.